Hello everyone. In the last lecture we have discussed about the fundamental principle of waveguide lasers and their working principles and how one can exploit bandgap engineering in compound semiconductors for demonstrating double heterostructure efficient laser sources, semiconductor laser sources that can be driven by just a current. Forward current will convert into laser output. And today in this lecture I will try to show that what is the problem in silicon. Silicon, in spite of semiconductor and in spite of huge success in electronics industry and also photonics, optical waveguides, etc., it is still a nightmare for technologists and photonics engineers to demonstrate silicon, demonstrate a laser source in silicon crystal itself. So, we will just try to discuss about what are the problems and if there is any prospects at all or not. So, and then we will try to see some of the how some of the light sources, how present generation of industry and technologists trying to overcome for some practical light sources which can be actually which is actually in fact integrated on chip for silicon photonics applications. Let us see what is the problem in silicon. Compound semiconductors are good and silicon crystals, silicon and similar material like germanium semiconductors, they are not good for laser emission. If we just try to see that two different type of band structure in semiconductors are available. If you just analyze all the semiconductors, you can find two different type of energy band structure for electrons. One type is direct band gap semiconductors, for which if you just try to see energy versus momentum, this EK diagram, so called EK diagram. K is the momentum vector. That means when electrons moves inside the crystal, it will have, it is like a wave, right. It is a kind of electron can be considered as a quantum particle, and quantum particle means its kind of wave nature will be there, and for its wave nature to analyze, you need to consider certain kind of wave vector. So, that means electron propagation you can express in k space, that means momentum space, energy momentum space. And if you just see that the energy normally, if you just think of energy of a electron, we express that E equal to h cut square k square by 2 m. This is actually nothing but half mv square, because inside crystal electron when moves, its kinetic energy is with a velocity v, kinetic energy is half mv square, but v actually this mv normally momentum of whenever we are considering a quantum particle with a wave vector k, then momentum of the quantum particle is expressed by h k and energy is normally h cut omega. That is what we know, that if momentum is h cut k, normally half mv square can be written as momentum square by 2 m. Okay. So, that is how P becomes h cut square k square by 2 m. So, that means for a free electron, if you are just considering a free electron, that means energy is h cut square 2 m h cut square 2 m times k square. Okay. This is the value. So, EK diagram it should be like a parabola. But when we consider this electron inside crystal, inside conduction band, inside valence band, this EK diagram will not be exactly like a parabola. It depends on which direction it is actually electron moving. Okay. Depending on the direction, you can see that some times the structure, instead of simple parabola like this, it can be something like this in a certain direction, the energy K structure. So, some of the semiconductors you will find in the conduction band, it is the bottom of the conduction band. Whenever you are just getting a EK diagram, for example, normal EK diagram, if you see here for free electron, it will be like this. So, this is E, this is energy, that is actually following these things. But you can think of this similar type of things in electrons in a crystal, and whenever you are considering in the crystal, there is a conduction band, there is a valence band. So, in that case you will see some kind of modification. I am not going into that detail, but when you check that some of the material, you will get conduction band spectrum like this, EK diagram like this, and valence band, it will be like this one, inverted parabola, because you know this is actually EV and this will be called as a EC, right. Earlier we have shown that band like structure, that is actually as a function of x, and this is energy at any position, what is the band. Now we are just expressing the band structure in k space, that is momentum space. Momentum space, that means at a particular direction k space, k in terms of k we are putting energy and k. This is energy and x, and this is energy and k. So, k is a vector, wave vector, it can have any direction, in certain direction if you move, and if you see that this is going like this, and maybe all the energy levels here up to here, it is all are filled with some electrons, there can be some kind of electrons. Okay. And here also all the energy levels, if you are just considering as k equal to 0 means some energy levels we consider, that is k equal to 0 means it is a little bit misleading, that means k 0 means momentum equal to 0 and electron will not be able to move like that, it is a fixed, it is not like that. So, it will be actually repeated periodic structures. So, in that point of view, if you just study a solid state physics book, you can understand more. But here we can say that this in the valence band, whatever the electron energy that follow this thing, and normally this energy is not for electrons, instead of that we consider that the energy for the holes. You can consider that, okay, because in the valence band we know in semiconductor particularly some of the electrons can go up to the conduction band and occupy the available conduction band energies, and that is what empty, and all other energy levels they are actually occupied. So, these are many, meaning if you just consider one electron here sitting here, it will have certain k value and this is its energy, and if we are considering this one, this is your k value and this is corresponding your energy. So, that means as you go for energy higher and higher, lower and lower, so it will be just occupying this side, and you go for there, you see some of the energy levels electrons are not occupied, and that electrons gone to conduction band, and that is why it is empty. These are called holes. And in this case, suppose at some point somehow you create that electrons, more electrons in the conduction band and more holes in the valence band, more empty space in the valence band. That is what we know, that is a population inversion. For example, we created, we discussed in the previous lecture, population inversion, something like that you have created. Maybe in PN junction you have given forward bias, and there actually you see that electrons, more electrons in the conduction band, more electrons in the valence band. And when you talk about more electrons in the conduction band, then their EK diagram, momentum, different energy, and what is their corresponding momentum should be, it is something like that, and valence band something like that. Population inversion, but they have to follow this thing, this energy, this dispersion relation, they should, all the electrons should follow. But normally you know in the conduction band, see whenever some electrons are there, they will occupy from the bottom energy to the higher energy levels, and when something will be emptied in the valence band, that should be in the top here, some empty things will be available here. So, if some electrons from the bottom of the conduction band tries to recombine to the holes that is in the top of the valence band, then you see directly it comes, and this is the k axis. So, the same momentum, electron here jumps to the conduction band, and it does not need to change its momentum, and then maybe a little bit of momentum can be changed. Okay. So, in that case it is actually directly when it comes momentum matching is happening, because in that case only energy is there, energy has to be lost, something to be emitted, and that energy will be coming like a h cut omega radiative energy, photon energy. And you know, if you just think about photon, photon is a quantum particle and its energy h cut omega, and if you just think of its momentum also, its momentum, because photon lambda is very large. According to the de Broglie hypothesis, momentum equal to h by lambda. H is the Planck constant, 6.626 into 10 to the power minus 34 joule second, very small amount. And since lambda is very large, momentum is also relatively small compared to lambda for the electron. Electron normally quantum particle, its lambda is very small compared to in the order of angstrom or so on. When it is considered as a wave packet, electron wave packet, that lambda is in the order of angstrom or so on. But in case of photon, the lambda we are considering corresponding to this energy, that is in the order of say maybe 1 micron or so. So, angstrom and 1 micron. So, in that case photon momentum is very less. So, when photon emits, it carries a very little momentum. So, that little momentum it can adjust when it is just a little bit of k difference is there and comes back to the valence band, it is matching directly. So, directly electron can come back from the conduction band and recombine to the valence band, and you can emit a photon. That is actually conduction, that is the thing happens for the direct band gap semiconductor. But some of the semiconductors you will find that if you see the conduction band EK diagram, it is not like simple parabola and where bottom of the conduction band is exactly matching to the top of the valence band. Rather, you see here is a value is there and additional value is there in some other k value, which is actually lower energy level. This is energy scale, lower energy level. So, whenever you are creating a population inversion, so your electrons in the conduction band will occupy this space with this momentum axis, in this momentum axis. But whenever you see the holes it will be emptied in the top of the valence band. So, that means if these electrons wants to recombine, this is in k space, remember that this is true for every position, even in the depletion region where you are creating a population inversion. So, these electrons if tries to recombine, it needs to adjust the momentum of this much, and to adjust this much, then only it can emit a photon. And you know that photon if you just think about this lambda, corresponding lambda and momentum, it is a very little bit of a momentum it carries. So, ultimately the momentum mismatch needs to be there if photons to be emitted, and that is actually against the law of physics. So, for any transition, any reaction to takes place, you have to consider two fundamental laws, energy conservation, momentum conservation. So, since momentum conservation is not there, so what it does a little bit indirect way. It takes help of phonon. Phonon means it is another type of quantum particle which is nothing but the lattice vibration. This actually causes because of the lattice vibration. So, that actually can have a very little energy, but it has a very small wavelength, it can have very small wavelength also. So, in that case it can actually give some kind of phonon emission. So, that means it can acquire some, it can lose some momentum to phonon and then it can recombine to the holes. So, it is an indirect way of recombinations, and if this electron, this hole and this phonon, all this quantum particle and photon, this is also quantum particle. So, all these 4 quantum particle to act together. So, they should come to a certain coincidence. that they should interact, they should have a good overlap, so that you can have this type of transition. And because of that, photon emission probability is very, very poor. But in this case, you have to deal with electron and whole recombined photon comes. So, at least you do not need any vias, phonon via. So, that is why photon emission probability is high. All the compound semiconductors are having this type of band structure, but silicon and germanium, they are having this type of indirect band gap semiconductors. Okay. So, laser emission requires direct band gap semiconductors. Silicon is an indirect band gap semiconductor. That is a problem. So, you cannot really it is a physics, it is a physical, the physics actually prohibiting that it is not easy to have your laser in silicon. But you know, this there is some technology, we can just try to engineer something so that get some kind of silicon laser or not. People are keep on trying for decades, and still very close to getting laser in silicon. We will just show how people are overcoming that, but long way to go still. Little bit of understanding comparison of gallium arsenide type 3,5 semiconductors and silicon germanium type semiconductors, which are very good for electronics and for other photonics type of devices. If you see that compound semiconductors, actually people got lot of optoelectronic devices including lasers and photodetectors, because of for any laser, any photodetector you want to demonstrate, this has to be defined first, which wavelength, what is the operating wavelength you want, and what is the required, accordingly you have to design. And for that purpose, we know that if you make different type of compound, we have discussed in the previous lecture, compound alloying different type of 3-5 elements in the periodic table, and then you can get different type of material of different band gaps, and that type of material you can actually grow. You can get different type of alloy structure and technology already available today, that a controlled fraction, controlled alloy composition, you can actually elemental composition in alloy you can have, and you can control the band gap. For example, it is shown here that the band gap actually depends on normally that is a lattice constant. Whenever some atomic structures are there in 3 dimensions, they actually maintain some periodic structure, right. So, this periodic lattice you can consider like that. Instead of that, it is like a whenever you are building a house, you need a brick by brick assembling. Similarly, when crystal is formed, in that case you can consider some unit cell, and that unit cell is extended in all 3 directions, then you can get an entire crystal. So, that unit cell or maybe in a unit cell, suppose you have a unit cell something like this, cubic unit cell something you consider, where some of the atoms are there some particular locations, and that particular things you are just extending in all 3 directions, you get the entire crystal. And for that unit cell, the length, if it is a cubic, if length is a particular length a, that is actually called lattice constant. That I think I am not going into the details, just giving you some idea. And if you see that in a alloy, that particular type of structures will be created, and that particular structure, whenever you are just making more and more composition, you are replacing some of the gallium with arsenic, with the aluminum, or arsenic with some kind of phosphorus, etc., then this type of lattice constant also gets changed. When lattice constant change, that periodic things change, then your band gap will be also changed. So, here it is shown very nicely that lattice constant in the x axis, this is not comma, this is actually 5.4, 5.6, 5.8, 6.0, 6.2, 6.3, 4, 6.6 angstrom. It is shown angstrom. 10 angstrom equal to 1 nanometer. Okay, 1 nanometer means 10 angstrom, 1 nanometer means 10 to the power minus 9 meter. Okay. So, all these small distance, when crystals are formed, their atoms are spaced like that. So, when I consider lattice constant, you can think about that it is a minimum distance between 2 successive atoms in the crystal. So, you see certain material, for example, let us try to find out in this map gallium arsenide here. Gallium arsenide, the lattice constant is somewhere here. It is around 5.7 or so. And what is the band gap? Band gap is this one. This is about 1.43 electron volt. 1 electron volt is 1.6 into 10 to the minus 19 joule, right, energy. Okay. So, you can have this 1.43 electron volt gallium arsenide, band gap is 1.43, that is why you get gallium arsenide this lambda g. If you use this formula, that means Eg equal to h cut omega equal to h c by lambda, omega equal to 2 pi c by lambda, h cut equal to h by 2 pi, if you just convert h c by lambda. So, then you can find out lambda equal to h c by E g. If you put Planck constant, velocity of light, etc., then you can get this expression, then you can get this lambda g, that corresponding to the band gap, the wavelength. If energy in electron volt, gap energy in electron volt, this lambda g can be micrometer, you can find out. Okay. So, normally this band gap, if it is 1.43, then lambda equal to, if it is this one is 1.43 electron volt for gallium arsenide, this lambda will be equal to, what do you call that, 850 nanometer or 0.850 micrometer. Using this expression you can find gallium arsenide. Now, you want to make alloy. For example, if you start replacing gallium with aluminum, so gas, for example, I just put gallium A aluminum X fraction by replacing gallium X fraction and arsenic, gas you are just trying to make. Then what happens? You are just your gallium atom, whatever the crystallographic structure gallium arsenide is there, I will just show what is their structure. Then you fraction of gallium, some of the gallium atoms are replaced by X. So, if X equal to 1, that means it will be aluminum arsenide. So, keep on increasing the fraction, then you will get aluminum arsenide here, gallium arsenide here and aluminum arsenide here. So, if you keep on increasing the X, that means aluminum content, if you keep on increasing, then you can get slowly to aluminum arsenide, another type of compound semiconductor, for which you see the lattice constant is also same. But at the same time, if you see y axis, it is going up, that means band gap is changing. So, if you are just moving from gallium arsenide to aluminum arsenide by changing this X fraction, then your band gap keep on increasing and you reach here. Now, again, if any path you take, suppose this gallium arsenide, this arsenic, if you are just slowly replaced by antimony, for example, this is gallium antimonide, then you can see that the band gap and lattice constant will change in this path curve. And then from here, if you want to consider that this gallium being replaced by aluminum again, aluminum antimonide, then it goes like this path. Or if you want, suppose gallium, some of the aluminum arsenide here, if you are just slowly increasing aluminum indium arsenide here, it will come like this. It can happen that different type of material, if you consider different type of position you will get, and different type of composition you will be getting, different type of lattice constant you will be getting and band gap you will be getting. So, by controlling the composition you can actually engineer the band gap. But thing is that controlling the compound, for example, if you want to go for gallium arsenide to aluminum arsenide, you see you do not need to change your lattice constant. When you do not need to change the lattice constant, that type of alloy creation is relatively easier. So, you can get a very good semiconducting material also for that. Okay, good quality crystal you can generate and you can engineer the band gap. So, normally if you just think of the different type of material, compound material, and if you position there also in the same chart germanium and silicon, it will be germanium position is this one, corresponding lattice constant is this one, and band gap if you see it is around 0.67 or 0.7 electron volt, and silicon, if you know, it is 1.12 electron volt, and band lattice constant is about 5 point. What is lattice constant? I will come little more details in next slides. So, in this case, you see whatever we have shown here in this slide, some of the lines, if you see, is dashed line, and some of the lines are solid line. For example, if I try to change aluminum antimonide, slowly aluminum being replaced by indium, then lattice constant is increasing as well as band gap is reducing, and up to here it is dashed line, and then it is shown as a solid line. So, from here to here solid line means it is actually direct band gap. The material compound you will be getting, that is a direct band gap material, and if you are just using in this region little bit of changing aluminum, that will be remaining like a indirect band gap semiconductor. So, indirect band gap semiconductors are not good for laser action. So, you have to choose a suitable compound so that it can become a direct band gap semiconductor. Here if you say silicon and germanium, they are indirect band gap semiconductor, but if you want to make a silicon germanium alloy, no way you can get, if you see slowly you are becoming silicon. For example, you can consider silicon 1 minus X, germanium X, for example, X amount of silicon being replaced by germanium. Then what happen, as you keep on increasing, that lattice constant is increasing and band gap is reducing, and then again it is changing like this. Okay. So, lattice constant changing, still you will be getting indirect band gap semiconductor. But nevertheless, indirect or direct, you can think of that. If you are just going back to this structure, okay, suppose emission is not possible, but what it can happen, suppose you have a like this, sorry, if you have some kind of additional photons coming. So, what happen, electron from the valence band can actually absorb the photon and can energize, and that electron can go to the conduction band, and then photon will get absorbed. So, you can see some kind of absorption, and this absorption can happen equally whether it is actually direct band gap or indirect band gap. Phonon assistance band gap is there, so it can actually get absorption also indirect band gap semiconductor as well. Even though emission probability poor, etc., but absorption can happen, even absorption can happen directly to here also. So, electrons can absorb sufficient energy from the photon, and it can come to electron here, and slowly it can settle here also. That type of absorption, indirect absorption can happen also. So, if I just only check about absorption, then you see that silicon absorption, as you keep on increasing your wavelength up to 1.12, if you see the absorption is getting reduced almost slow, and beyond that almost no absorption. That means above 1.1 micrometer silicon is showing transparency, below that it is getting absorbed, because photon energy is actually absorbed by electrons from the conduction valence band and go to the conduction band, electron jumps to the conduction band. Similarly, for gallium arsenide, you see here up to here. So, this is actually corresponding lambda g whatever we calculated. Here this is corresponding to lambda g for silicon, and when lambda g is lower than that, meaning photon energy is higher, so that photon will be absorbed. That means, when it absorbed, electron hole pair will be generated. We will see that electron hole pair generation is necessary for photo detection. I will be discussing that thing, but here we are discussing mostly for laser. First I will be discussing that why silicon, what is the problem we have discussed here, and the actual situation, why silicon indirect band gap semiconductor, and whether that can be overcome or not. After that we will come back to the photo detection purpose. So, but if you see germanium rather than here, if you see, it can actually go up to 1.6 micrometer it absorbed, and beyond that it can attenuate, it is transparent. And you can get indium gallium arsenide phosphide, which is actually very good for laser emitting at 1550 nanometer wavelength. So, here if you see that the band gap is around 1.4, and laser emission when takes place around before above 1.5 laser emission can happen. Okay. So, different type of material it is shown absorption coefficient. Okay. Now, why I am showing this, one interesting part is that for ideal photonic chip you need laser diode for photon emission, waveguide same photon should be transparent. If you can choose a certain band gap where laser electron photon recombine and gives you photon emission, but on the same material the same photon can get absorbed as well in a reverse process. So, electron hole recombines and give you photon, and that photon while traveling it can give up energy to the another electron from the valence band, and that electron can go to the conduction band again. So, this is actually contradicting. If you want to have a material where you want to have a laser diode photon emission, that cannot be good for waveguide, because the photon can reabsorb. For waveguide you need low loss, absorption should be free, and at the same time again photodiode photon absorption require. So, you need material where photon emission require, photon absorption required, and also photon transparency required. It is a very difficult to get a material with a normal simple structure where you can get all the three simultaneously. So, for ideal optoelectronic circuit where you want to integrate laser diode, photodiode, waveguides, modulator, etc., it is a very challenging task. It is only you can solve by different type of technology. Physics actually is not, is prohibiting that same material can simultaneously give you laser diode and waveguiding and photodiode already. Obviously, laser diode, if you have a laser diode fabricated out of a semiconductor, because it is a just emission of photons, and photodetector is the just absorption reabsorption. So, maybe photodetector and laser diode, photodiode and laser diode can be fabricated in a same material, but the same material we cannot use for waveguide transparency. So, what is that? How that is possible? Band gap engineering is the only solution. So, band gap engineering meaning wherever you need laser source, you just engineer the band gap so that photon can be emitted, and wherever you need waveguiding, you should engineer the band gap so that that photon can be transparent, band gap can be just relaxed. And again whenever you need a photodetector, that time that region you need a again band gap engineering for making your detection. So, that means on chip, if you want to have an ideal photonics chip where source, photodetectors, everything can be integrated, so you must go for band gap engineering. So, that is actually the technological challenge for the industry, for the academicians like you. You have to find out the different type of ways out. Let us see what is the state of the art. Okay. So, now to discuss about that how people are thinking to demonstrate silicon laser, we need little bit of crystallographic structure to understand for silicon, whether the silicon-germanium alloy band gap engineering possible to make it certain kind of possibilities or not. Already we have shown that even if you are just doing silicon-germanium alloy, experimental evidence shows that earlier diagram we have shown that they never come up with a direct band gap semiconductor structures, but people tried different tricks. Let us see. So, if you see the crystallographic structure for silicon and germanium, they are looking like this. Unit cell, if you see, it is like a cube, as I mentioned that a crystallographic structure, it is a building block, is a unit cell. You can extend this x direction, y direction, z direction, then it is just you can get a entire structure. And this is a cube, and this is actually each of this cube distance we consider as a called lattice constant. And if you see if you just consider that some circles, these are actually silicon or germanium atoms. So, these are the position of the silicon, or if it is silicon crystal, silicon atoms, if it is germanium crystal, germanium atoms, their positions are shown here. And you can consider that, you see, these are the position, if it height is there. So, this atom, this atom, this and this atom, they are considered like a square of a square if you are consider base point. So, one atom is here, one atom is here, one atom is here, one atom is here, one atom in the center face bottom, and identical situation in the top here, and this surface also is there. So, that means every surface, there are 6 surfaces for the cube, every surfaces there in the center one atom, and all the corners of the cube there will be atoms are there. And apart from that, you see additional one atom is there coming like this here, that is actually position something like that if you are considering here. So, if total height, if this height is 1, if you are considering this atom is around, all these atoms are 0 position, 0 0 position, 0 0 position, 0 0 position, and this height will be, this is also 0 position, this height will be 1/4 position at the height. So, this means this gone to 1/4 this side, this 1/4, and height also 1/4 this side. So, basically each of these atom, again if you see, they are covalently bonded with 4 other atoms like this. This is the structures, and we can consider that this one is a particular lattice point. This atom and this atom can be considered combined to consider a particular lattice point. With particular lattice point, one atom is here and another atom is here. And if you just see that every lattice point, you can just consider one silicon atom and club to this thing, and then you can consider something like that FCC crystal, face center cubic crystal. Face center cubic crystal means you will have all corners atoms will be there, in the face one atom will be there, but you can consider one corner one atoms associated with another atom, 2 atoms are there, and in the face also one atoms associated with another atoms are there. So, that type of situation if you are considering as a unit cell, and that unit cell you extend x direction, y direction, z direction, then you can get the entire crystal for silicon and germanium. Both silicon and germanium crystallographic structures are identical. Only thing is that for silicon the lattice constant, this distance is about 5.43 angstrom, and for germanium little high, 5.66 angstrom, 10 angstrom meaning 1 nanometer. And silicon electronic structure, if you see, there are 14 electrons, and out of them these 4 electrons are actually valence electrons, and germanium there are 32 electrons, and you see these 4 electrons are the valence electrons. So, germanium atoms are relatively little bit more number of atoms and electrons, and its size will be, obviously it will be different compared to silicon. So, that is the reason when you see the crystallographics their band structure EK diagram, then you can see it is a very complicated mathematics, it is a kind of quantum mechanically it is normally solved, because you know this kind of interaction of this electrons interaction, suppose electron belongs to this atom, that can be that can have some kind of influence of the all the neighboring atoms, all the surrounding atoms. So, those things you have to consider. So, any electrons inside the atom, it interacts with its nucleus, and also it can be influenced by neighboring atoms also. So, how they are arranged, depending on that you have to solve, and there are various methods are there. One of the methods is K dot P methods, chronic Penny models, very approximation method, tight binding approximations, and very lately people are using density function theory also, DFT, density function theory. So, using that people can actually reproduce the band structures. So, whenever you just consider EK diagram, energy, and K momentum wave vector, this K is a wave vector, you can have a different direction, right. So, different direction you define normally in a crystallographic structure. If it is a crystallographic structure, this is your particular direction, we call it 100 direction, either this direction or this direction, they are identical direction. We can consider this is like a 100 direction, either x axis, y axis, z axis, they are identical situation for this. But if it is diagonal direction, we are considering that is actually 111 direction. And different direction crystallographic structures are there, but for here in this course I am not going into the detail, just you can consider that different direction, if electron if you try to transport electron in different direction, it will see different type of periodicity, different type of situation. So, different type of energy EK diagram. If you are energizing electron to move in a certain direction, it will see different type of dispersion relation, and if it is going another direction, different type of situations. So, here it is shown that around 100 direction, if you see the valence band will have also different type of curve, will be there. Electron can follow this curve, or maybe these two curve, very fine structures are there. All these are coming from complicated mathematical solutions. Normally computer aided solutions are required. I am not going into that detail again. And you see this EK diagram, it is not like a parabola I have shown earlier, right. It's completely different. One side is asymmetric, one side means it is showing in the x direction, another side is not minus x direction, because x direction minus x direction is identical. If you go for different direction, say that is called 111 direction, that means diagonal direction, then you can see that minimum is coming, and 110 this minima is coming, and you get a maxima where the energy, allowed energy is highest here, that particular point which is called gamma point, and along 1 direction you can find a particular k value that will be minimum here, and x value it is minimum here. And then next higher band, if you are just trying to see, then also you can get different type of features for germanium, here it is shown, and you see that one next higher band structure, the EK diagram, it is showing that you can see there is a valley exactly matching to the gamma point here. This is a gamma point, it is shown, and it is the energy of electrons is minimum. But if the electron, if you see the k vector you are considering along 1 direction, you see this is the coming down like a valley, but this valley is lower than this one. Okay. So, that means your this is kind of indirect band gap semiconductor, because top of the valence band and bottom of the conduction band, this is a bottom minima. If you see, this is also minima, but this one also minimum lower than this one. So, we have to consider any electron in the conduction band, they will try to occupy this valley first. So, bottom of the conduction band and top of the valence band not matching exactly at same k position. This is actually k along x direction, this is along 111 direction. Okay, 100 direction. If you want to know what this direction defines, different direction means, you can just again consult any solid state physics book, maybe NPTEL solid state physics book, you can also check that one. So, this is indirect band gap semiconductor. Similarly, for silicon, if you see compared to germanium, if you see that valley of the conduction band, that is along in the x direction, 100 direction. 11 direction. Just remember that 100 direction, it is a class of direction. It means it involves either x direction, y direction or z direction. All direction are 100 class. They are identical. But other than this direction, if you are just considering any other direction like diagonal direction called 111 direction. Okay. So, that is actually will be another minima you will be getting here, here also you are getting minima, but conduction band you will see along x direction. So, that is the difference basically for silicon and germanium. The conduction band minima happens in silicon along x direction. In the k space, by the way, this x direction means when I consider 100 direction, that means kx I would consider, that means x component of the k vector. So, both silicon and germanium are indirect band gap semiconductor, but their EK diagram band structures are not identical. This is not identical because their electronic structures are different, their lattice constants are different. Okay. That is why you are getting this thing. So, if you analyze different type of semiconductor, different type of crystal, different type of band structure you will be getting. These are very complicated. So, I think if you are studying solid state physics, you can go much more details, but for this course, for engineering purpose, you can take this is all about whatever it is shown here, that is it is true, it is granted. Okay. So, now if you see, as I have shown earlier, that as a function, if you are making a silicon germanium alloy, as you consider this silicon content, for example, if you start with a germanium and keep on increasing silicon content, then you see if silicon content is 0, then you can get band gap is around 6.5 0.67 electron volt or something like that, 0.65 electron volt or something like that. As you keep on increasing silicon, because germanium normally the band gap, if you just check here, this is the band gap, this will be called as a band gap. This is your energy in electron volt, this is 0 and it is about 6 point band gap. But for silicon the band gap is this one, EG band gap is this one, this is about 1.12 electron volt. So, when you are actually increasing your silicon content, initially starting from 0, your band gap is 0.65 electron volt. Now, increasing silicon, that means you get back your energy value still will be this one, and keep on increasing silicon content more and more and more, then what happens, this thing slowly the alloy, whenever you are just increasing germanium to silicon, so the property moves from germanium property to silicon dominating property. So, silicon dominating property, maybe it will come to this value, X value. This is called X value, bottom of the conduction band, this is L value of the conduction band, and that is the reason you see initially your band gap is increasing, but with a certain slope, and at this point actually what is happening, it is a confused state. So, whenever silicon percentage is around 20% and so on, that means which value will be dominating, because silicon content is slowly increasing, even 20% of silicon content that pull the band structure to the X value. That means 100 direction, the band gap will be there and the slope is different, but band gap is increasing and up to 1.10. It is 1 means percentage is when silicon is completely, germanium atoms are completely replaced, all the atoms of germanium component, germanium atoms are replaced by silicon, that means silicon crystal. So, band gap will be 1.12 electron volt. If you want to know little more about that, you just go to this paper and download that thing, and how it is calculated, band structure, etc. You will be able to learn that thing. It is a very old paper, 1958. So, about 42, about 65 years ago, 60 years ago. Now, very recently, so now what we conclude, that even if you do alloy, it is not like compound semiconductor, some of the fractions you will see the direct band gap semiconductor. You indeed see band gap engineering, but this band gap is moving from L band to X value, L value to X, L value to X value, L value to X value, the conduction band, and valence band it is remaining identical. So, that means even if you are making alloy, band gap is moving from 0.65 electron volt to 1.12 electron volt, that is fine, but it is only conduction minima just moved from L value to X value, remain identical, indirect band gap semiconductor. So, there is no way that some of the compound semiconductor, like I have shown earlier, that if you just make some alloy, you can get some fractions which can give you direct band gap semiconductor, and some fraction, some composition can give you indirect band gap, but silicon germanium it is not possible. So, unless and until you get a silicon germanium direct band gap in silicon or silicon germanium alloy. Why we are talking about silicon germanium alloy? Because silicon and germanium, this type of alloy is well known for CMOS industry, and they are used largely used for various type of electronic devices. So, it is CMOS compatible. So, first try would be just go for band gap engineering, particularly for photodetector designing, etc. But what we understand that is not giving you direct band gap semiconductor. So, laser also not possible. So, what is the alternative way? So, people are trying that why these indirect band gap semiconductors? That is because of the special crystallographic structure, that is a FCC crystallographic structure, phase center cubic, this type of unit cell. If you can grow silicon crystal little bit differently, right, technologically, if you just grow, this is a natural silicon, if you grow silicon crystal silicon is of course normally whenever you use in electronics industry and photonic industry, that silicon crystal you have to grow. But this growth technique, natural growth technique is like this cubic crystal, something like that. Now people tried that okay, if we can grow little bit differently, different arrangement of atoms, if that is possible or not. So people tried, instead of cubic crystal growth, like whenever you see cubic silicon, the band structures are looking like this. This is a valence band, and this is your conduction, this is silicon conduction band will be coming like this, right. And cubic germanium, if you grow, the structure is shown here. This is a gamma point, this side is shown as X, this side is L. Normally you know this is your shown X and this is L. It is actually reverse process here in this paper. You can find a detail in this paper. This is recently published in Nature 2020. So they calculated band structure of a cubic silicon using density function theory, and this side is shown L because it is your silicon along yes. So silicon, this is actually L direction and this is X valley. Here is your band value is coming along X direction, and this one actually 1.12 electron volt. And for germanium, if you see this one actually this to this, that is actually your band gap, and that is band gap is equal to less than 1, it is about 0.6 electron, 0.65 electron volt or so. So this is actually a L value. For germanium you have a L value in the conduction band, and for silicon this is actually silicon here, and silicon what you get here is actually silicon, yes. So here you see in the L value germanium is there in the conduction band. But if you can actually somehow grow silicon and germanium with hexagonal crystallographic structure. What is that hexagonal crystallographic structure? It is something like that hexagonal crystallographic, like zinc oxide. If you see crystallographic structure of zinc oxide, then atomic arrangement, if you see that it takes a hexagonal shape. If you see this one, this is your lattice constant, here all the hexagonal something like this type of shape it will take. Atomic positions it takes like this. Okay. So if you can grow silicon and germanium like that, that is also possible. It depends on your crystal growth technique. If you somehow engineer your crystal growth technique, normally all the silicon crystals, most of the crystals, they are actually grown using Czochralski method. That is a well known method, Czochralski method, and that is a natural process, whatever I have shown here, cubic crystal growth. But if you have some kind of special type of seeding mechanism is there, so that you can grow all the atomic positions like a hexagonal structure like this. So here it is shown zinc position and oxide position, and in case of silicon, this all zinc and oxygen all will be like a silicon atoms. So this white dots and white balls and black balls, they are shown as atomic positions. So instead of zinc and oxide, you will be getting always silicon crystal, or if it is germanium, you will be getting germanium crystal. If you can grow like that, then if you again calculate your density function theory for band structure, then you can see that the band structure is completely different. How it is? For silicon, if you see that you will have another particular locations, all these points are actually defined points in the K space. I am not going into the details of those space, but what you see that your valence band is somehow little bit modified compared to this one. You see valence band, it is modified like that, and your conduction band, you see the minima, instead of X value you will see M value, some other location, other direction you will see. Okay. Hexagonal, if you just grow, and if you just grow hexagonal germanium, then what happen? This type of crystallographic structure if you grow, then also your band structure different. This is your all the fine lines, all this corresponding to the valence band. This is around gamma point, and in germanium instead of your value in the L, in the modified structure, if you see that the value comes here directly here, exactly at the gamma point. Okay. So, it is looking like as if it is something like coming like a direct band gap semiconductor for germanium, right. So, actually if you actually speaking, if you see all the structures, if you see, ultimately it is very difficult to grow the direct band gap semiconductor. Even if it is hexagonal, it has been shown that the silicon and germanium, they are basically indirect band gap semiconductor. So, what is the way out? If you make a alloy, now if you make alloy structure like silicon X fraction you remove and germanium X fraction you remove, and you grow a crystal silicon germanium alloy, you get a hexagonal crystal like this. You see, according to the growth, these are the pillars grown, and it has been shown that this if X is somehow greater than 0.65, that means if germanium content is more, silicon X fraction reduced germanium content is more, then band gap engineering is possible. At the same time, you can get a direct band gap semiconductor. So, in this lecture, what we try to make you convince that just silicon crystal indirect band gap, FCC cubic crystal, silicon crystal, germanium crystal, it is a indirect band gap semiconductor. But if you grow with a hexagonal structures like this, the atomic arrangement such that the band structure can be engineered, and even after engineering you cannot get also direct band gap semiconductor. But if you can try to make silicon germanium alloy with hexagonal structure, then you can get a direct band gap semiconductor, and clearly direct band gap is predicted at the gamma point with a magnitude that is tunable across 0.3 electron volt to 0.7 electron volt. So, if you see all these points, these are the valley points, M valley, L valley, U valley, gamma valley in the conduction band. If you increase your germanium content, okay, the gamma valley, actually if you see increasing germanium content, gamma valley will be lowering down. This is gamma, red one. U valley, L valley, M L, that means you can actually engineer the band gap, right. And if you make a population inversion, that means electron in the conduction band more and holes in the valence band more, then radiative recombination will take place, electron and hole. So, depending on the X fraction, X equal to 1, 0.875, 0.75, 0.625, if you go on decreasing a X value up to 0.625, more than, that means all the X greater than 0.65 we have shown, then you see that lifetime recombination lifetime or radiative lifetime, that means how much time it takes for radiating a photon, it is slowly coming closer to the gallium arsenide. And gallium arsenide, you know, that is actually like a direct band gap semiconductor, well not for laser. So, that means if you make a silicon germanium structure and band gap engineer with hexagonal crystallographic growth, then you can get a laser emission, and it is calculated and it is shown that you see as a function of X, then what is the transition luminescence, photoluminescence, whatever coming out of that type of silicon germanium crystal, different energy level, different energy you can calculate, already electron volt is there, that means lambda you can calculate in micrometer, that already 1.24 by whatever Eg electron volt. So, corresponding energy, corresponding lambda, you can find out that emission will be there. So, that comment I just pointed out from this paper, this is a nice paper recently published, if you are interested, you download and read this paper. The spectral interval is of technological interest for many potential applications, including optical interconnects in computing, silicon quantum photonic circuits and optical sensing, among others. So, this is very including interconnects, all those type of thing I mean to say that. So, this is a very new prospect for silicon laser, but so far this is still, it's a, you see, this is just a coming out technology. I hope it will be dominating in future. It is upcoming technology for sure, but for the industry application purpose, it is now still, it is a long way to go. Normally people used to have different type of integration technique, that means hybrid integration of 3-5 laser sources. Now people are considering. So, there are 3 different technique people are using for hybrid integration. What are those? So, you can have for silicon photonics, photonic integrated circuits I mean to say, the practical light sources for on chip silicon photonics. So, direct mounting of 3-5 dies. So, you make your 3-5 wafer compound semiconductor which is capable of certain laser emission of interest. That dies you can just put directly on the top of the silicon photonics chip, and then you can bond them. It is a kind of pick and place precisely, and then you can actually fabricate, you can structure your laser by different type of process technology, and then you can bias wiring, everything you can do, and then light can emit and couple into the silicon waveguide. I will show that. And another thing is that wafer bonding based on heterogeneous integration. You can do that, okay, silicon wafer, and then you can grow. You can actually bond 3-5 semiconductors directly onto it, and then you can get a structure your laser, and you can make also photonic waveguide in the silicon. So, all this type of thing hybrid integration means, as I mentioned, that you cannot find a suitable material where you can have laser, photodetector and waveguide, good low loss waveguide in the same material platform. So, that is the one problem. Only possibility is that bandgap engineering efforts are going on. Alternatively, people are thinking that off chip laser or on chip hybrid integration. So, 3 different techniques are used, and one of them I will be just explaining here how it is coming like that. If you say 3-5 die is just bonded here, indium phosphide substrate removal and then processing 3-5 devices. So, you can have a compound semiconductor grow on indium phosphide crystal, okay, for necessary bandgap, engineer bandgap compound semiconductor, and then you just bond it, and then indium phosphide back layer, sacrificial layer you remove, and then you can structure them, process them and make a laser device. And that laser, if you fabricate, if you just see the SOI substrate, this is your SOI substrate, silicon substrate, barium oxide box, and this is a waveguide layer, and you can have some kind of mechanism so that laser emitted laser can be coupled into the waveguide layer. Okay. So, these things actually known for long time, since 2007, about 15 years ago, and that is still continuing, and technology is becoming more and more mature. So, that people are getting on chip laser sources. All right. So, you see sometimes you see the Fabry-Perot laser diode, how it is just mounted here, and this is your SOI waveguide inverted inverse taper is there. So, light from the normally laser when it emits, like a cross section is in the order of micrometer or so on, but you know silicon photonic where the cross section is some micron. So, normally inverse taper you do as a spot size converter, and in the top of the cladding of the inverse taper region is just some kind of polymer waveguide they use, and then emitted laser light slowly couple into the silicon laser. So, this is a kind of expensive technology and precise alignment, all those type of things are required, but still people have optimized those type of solutions, and they are getting and coming out with a products also. And you see this is the after on chip laser mounting etc. processing, it is shown that as a function of current how much power actually being coupled into the silicon waveguides. And here another interesting technique is very recently, it is known for a couple of years, that it is something like that. If you have a 3-5 semiconductor laser and you have a photonics chip, optical waveguide silicon photonic devices are there. If you want to couple light, why not like something like that electronic wire bonding? Whenever you do you go for packaging electronics chip, normally you have to bond your devices, you have to wire bond from your one device to your outside world. You need some kind of pins, like op amp, if you see there are pins outside, inside there is a bonding methods are there, but there is a electrical connection is there, electrical where you are just bonding, that technology is there. So, people have been trying to have similar type of bonding technique, so waveguide bonding. So, that means one waveguide to another waveguide, how you can couple light. So, can we have some kind of technique that okay, you just touch something and some wire type, that optical waveguide wire you can have, you can just bond in one waveguide, you can have a contact pad and then you can bring it to another waveguide and you can couple that thing. So, in that case, if you have a two different chip, one is 3-pipe semiconductor chip where you have photodetector and lasers is there, and another chip is silicon photonics. If you want to get laser output from there and directly connect into the another chip, just with a machine, if you can do that, that would be fantastic. So, there is a machine actually, that the lithography technique called 3D lithography technique. So, 3D lithography technique means you can have a laser source, and that laser source normally when we do photolithography, you know that normally you have a substrate, and then suppose this is your substrate, then you have a photoresist, you do coating, and then whenever light is falling, if it is a positive resist, that positive resist region actually it will be hardened, rest of the regions actually it will be dissolved in a developer and you get a structure. That means photon actually activate this polymer, like photoresist is kind of polymer, and that particular structure will be hardened, and other, this is your photon coming, right, this is photon beam or light beam is coming, and that region will be hardened and rest of the region will be developed, and you get a particular structure, defined structure where you want to do for etching and so on, you can do that. Similarly, this type of machine is has been invented where actually whenever you are focusing a laser light in a certain type of polymer, in the focused region, that polymer will be actually polymer chain will be modified, and that will be hardened, and if you develop that particular region will stay and the rest of the things can be developed. And this machine actually it is called 2-photon polymerization, TPP, 2-photon polymerization, TPP. So, when you focus a pulsed energetic pulsed high energy pulsed laser and focus it, then 2 photon jointly transfer energy to the polymer molecule, and when 2 photons transfer the energy to the polymer molecule, that polymer molecule will be modified, hardened, and wherever that is hardened, it is a focused laser beam using a inverted microscope. Some microscope is there, objective is there, you are just tightly focusing the laser source, and because of the 2-photon polymerization you can actually modify. Now, you can control that beam spot by computer programming, and you can actually wherever it can be 3-dimensional, you can actually define your structure. So, what it is done, for example, you have a chip 2 here and this is chip 1. Let us consider that this is your 3-pipe laser made out of gallium arsenide or indium phosphide, and this is your silicon photonics chip. So, what they do that entire region they coat with a polymer, thick polymer, in this case it is SU8. A special type of polymer is used for lot of structuring and different type of microfluidic channels, etc. People use that type of polymer. So, that type of polymer it will cover thick, maybe couple of microns or so. Now, this laser beam comes here. So, you can use this laser spot size to define a certain type of polymerization, 2-photon polymerization. You see this pink color things are there. So, as you move your spot size, focused beam as you move your focused beam from this region to this region, for example, this contact pad region, then you can see that that particular region will be polymerized, and if you put in a developer, then rest of the region it will be removed, only that hardened portion will be staying back. And you see the technology is so precisely optimized, you can see that this side one waveguide is there, this side another waveguide is there, on the top you have one waveguide, it is coming like that, it is bonded, this is a polymer waveguide and comes here, and in this there you see two chips separated by the gap here, and you can have connecting here. And then when light comes here, that can be evanescently coupled to this type of polymer waveguide, which is actually can be fabricated using photonic wire bonding, so called photonic wire bonding method, and you can get this type of thing. It is like a as easy like whatever you use for in electronics chip bonding. Actually in PCB, whenever you are mounting a electronics chip in PCB, a printed circuit board, there also you need to bond that different type of contact points of the electronic chip, you can bond with a PCB, or maybe chip to chip you can do that. That type of technology is well known and widely used for electronic industry. Now similar type of technology is being actually demonstrated for photonics industry, where you can have you can actually combine, you can actually bond from one particular photonics chip to another particular photonics chip. So in that case you do not need to go for all this type of complicated integration methods, etc. And here it is shown that the coupling between one waveguide to another waveguide, that polymer waveguide to photonic wire waveguide, it is a coupling loss, transmission loss, if you see it is less than 0.1 dB and so on for entire wavelength range. So that is a very promising technique, that is why I thought of sharing with you, so that in future whenever you are learning and going for research in different direction, that would be helpful for you. And yeah, using this technology, it is just they have already demonstrated some kind of so called photonic wire bonding for DWDM application purpose. If you see different type of lasers, they are fabricated out of indium phosphide chip. So they can be different color, maybe 16, 24, 32 and so on, different type of color they can be emitting, and you can actually bond with modulator, silicon photonics modulator chip. You see modulators can always, you can fabricate a very good low loss waveguides and modulators in silicon, and you can bond here, and then again you can use another chip where you can actually use for multiplexing purpose. Normally arrayed waveguide grating structure is used. Suppose you have hundreds of channels are there, hundreds of modulator you fabricated in silicon chip, where you can actually encode all your data, you can actually multiplex into them together into a single mode fiber, and you can take it as a use it as a for long haul communication purpose. So this is some kind of state of the art futuristic artistic think people are talking about, and very recently it is coming up very nicely, optimization, etc. And it is shown that this type of bonding, this photonic wire bonding, PWB means photonic wire bonding, how they can precisely control with computer. Nowadays computer technologies programming is so fast, so that you can precisely control your focused beam, and then you can bond. You see this is how nicely it is bonded polymer waveguide into the silicon chip, photonics chip, it is shown here. And you see this is how angle precisely 85 degrees controlled, and they have fabricated, you see they have two different chips where lasers are there, and this is the photonics chip, and they try to bond maybe 1, 2, 3, 4 different chips bonded here, and they have just shown how their insertion loss, that means whatever power on chip it is emitting here and how much being coupled to the silicon photonics chip, it is shown here. Just loss is in this case 0.6 dB, 0.6 dB, 0.4 dB, as low as 0.4 dB loss, coupling loss 0.4 dB only. So that is actually very phenomenal results. Basically whenever you talk about fiber coupling, for example standard single mode fiber coupling into silicon photonics chip, I think losses is 6 dB, 7 dB, and best possible loss people reported so far is 3 dB or so on. But in this case you see that this coupling loss is very small, just 0.4 dB, as small as 0.4 dB. So that is very interesting technology coming forward. So in next a few years I hope this technology is being flourishing, is going to be flourished. With this I just stop this lecture today, and in the last lecture I will be discussing about how one can integrate the photodetector, that is the first final things. So, you need passive devices, silicon photonics passive devices, modulators, lasers, and then final thing is the photodetector, and that is how we will be closing our courses. Thank you very much.